Hi and welcome to this next video from the Numerical Methods section of the A-level course. In previous videos we've looked at change of sign method as a way to identify a range in which values in which a root can lie. We then looked at iterations and a method for actually finding the root. Now we're looking at something called Raphson method, which is another method for locating roots. Now the Newton in this is Isaac Newton. He came up with the idea initially, and then 5 years later a guy called Raphson came along, and essentially what he did was just kind of tidied it up and rewrote it as a kind of iterative formula, which apparently is enough to give him credit for this. Lucky duck. Anyway, so this is it, Raphson, and let's have a look at what we have to do. So we're going to look at the method for finding a root. So here we go. Let's have a look at some function which has got a root. We're going to call that root alpha, and let's make our first approximation. Let's just take a guess. So our starting point is at x0. What we're going to do then is take that point at x0 and draw a tangent. That's the blue line that's just appeared. And the tangent to the curve, you'll notice, cuts through the x-axis at what I'm going to call x1. And it's much, much nearer to the root. And so it's a better approximation. And so what we'll do now is take our value x1, repeat the process, come up with a tangent at x1, and you can see again on our purple line now we're getting a value here which we might call x2, which again is getting closer and closer to the root. So if we keep repeating that process, drawing repeated tangents, then we will end up hitting our root. So what we need essentially is a method, mathematical method for describing or calculating that process. And you might be thinking, well, that's going to be a right pain in the backside, but it turns out to be a little more simple than you might imagine. Let's go back to our first point. So we've got x0, our starting point, and we've got x1, which is the point where our tangent hits the x-axis. What I'm going to do first of all is say, well, okay, let's think about how we would calculate the gradient of the tangent. Well, clearly the tangent is a straight line, so finding the gradient of a straight line is simple enough: y2 minus y1 over x2 minus x1. So let's do that. So we've got y2 minus y1, so that'll be essentially the distance of that line there. So we've got the y coordinate at this point, which is fx0, and the y coordinate here, which is just 0, and then we've got the x distance, which is going to be x0 minus x1. So there we go. So there's a method for finding the gradient. Let's just put that to one side for a second and say, well, we could also do it by differentiation, because we know the gradient of the tangent is the same as the gradient of the curve at the point x0, so we can quite simply say that our gradient is f dash x0. Right, so what we've got now is two ways of being able to calculate exactly the same thing. So these two expressions can be put equal to each other. There we go, so we've got f dash x0 equals fx0 minus 0 over x0 minus x1. And what we need to do, we're looking to calculate x1 using our initial value, which is x0. So you'll notice the expression x1 is sitting there. All the other bits are in terms of x0. So if we just rearrange this and make it say x1 equals, you end up with that. So in order to calculate x1, it's just x0 minus f of x0 over f dash x0. And that's going to form the basis for our iterative formula, because then the next one would be x2 equals x1 minus fx1 over f dash x1, and so on and so on and so forth until it turns into that, and that is your Newton-Raphson formula. Now, in my head, I always get confused or kind of struggle to remember which way around this fraction is. Am I putting the gradient on the top or the gradient on the bottom? The gradient function, the differentiate function, goes on the bottom, but never fear, that is given to you in the formula booklet, so you've always got that to look back and check on. So let's have a look at how this would work. So we've got a function there, f of x equals ln 3x plus 2 minus x squared cos x minus 3. And first of all, we've got to show that it's got a root in the interval 1.8, 1.9. So the way to go about that would be change of sign method. So let's start there. So f of 1.8, plug 1.8 into all of that, remembering that your trig function is in radians, and we get a negative. F of 1.9, put that in, you get a positive. And so there's our change of sign, and there's our statement. Change of sign and continuous, hence there's a root in the interval 1.8 to 1.9. Okay, so that's part A done and sorted. That's standard stuff. Let's go on and have a look at part B. Now, the first thing we're going to need to do for Newton-Raphson is do the differentiating. So let's get that done and out of the way first of all. So let's differentiate ln 3x plus 2, and if that's fairly straightforward, 3 over 3x plus 2, minus, and we've got to now differentiate that. We've got a product, so that's going to be a product rule job. So differentiate product rule. I'm going to just come out over here and just do a bit of fiddling around to make sure I've got that right before I put it into my final expression for the whole thing. So we've got differentiate the x squared, leave the cos x alone, leave the x squared alone, differentiate cos x, not forgetting of course it becomes minus, because differentiate cos you get minus sine. So that's that bit sorted. Put that into there, and then differentiate the 3. We haven't got to worry about that. And then finally a bit of tidying up, bearing in mind we've got a minus there, making that thing there a plus. And there it is, there's our expression for the derivative, for the gradient function. Right, we've now got f of 1.8 is 0.26. We already had that from over here. That's already been done as part of our change of sign. F dash of 1.8, let's put our value of 1.8 into that expression there. Sorry, I've expression that one there, so I'll tidy that one, apologies. And we get that value there. So now let's put that together in our Newton-Raphson formula. There it is, and then it's just a case of plugging it all into the calculator, and we end up with our first approximation is 1.860. Now, Newton-Raphson does tend to work fairly quickly. You find the root quite quickly. We could go for a second iteration, but what you generally tend to find is in the exam they're only going to ask you to do it once just to demonstrate that you know the technique. There's no point in doing repeated number crunching in an exam situation. So there we go. There we go. We've got our improved estimate, estimate for our root 1.860, and there we go. We're sorted.